This is Sean Burke, your instructor for Nutrition 150. We're going to go over the PowerPoint on energy expenditure. This video should help you a lot because there are some things that in my online class I don't worry about quite as much as my campus-based class, but I use the same PowerPoint. So I just want to make sure you don't try and understand some of these things that are a bit complicated to explain. So here we go. Okay, so why do we want to measure energy expenditure? Well, we want to measure it for training and dietary regimes for athletes and for the general population, as long as exercise prescription, right? We want to know how to lose weight, gain weight, change our body composition, those sort of things. We want to understand the metabolic and energy requirements, both for rest and for exercise, right? We also want to know about the effectiveness of exercise training to improve all sorts of fitness and health parameters. Okay, so the easiest, not really the easiest, but the best way to measure energy expenditure is called indirect calorimetry. So it measures oxygen and CO2 expiration, right? And so most of your energy expenditure is derived from from reactions with oxygen. So if we measure the amount of oxygen that you are using, we know how much energy you're using and what your metabolic rate is with a very high degree of accuracy. Okay, so the basic way we measure that is measuring the oxygen. We can also calculate how much one person burns at rest. It's mostly dependent on your body weight. Okay, and what we use, the term we use is 1 MET. So a metabolic equivalent is the resting energy expenditure of an adult, right? And so the resting energy expenditure of me, I weigh about 180 pounds, is going to be far different than somebody that weighs, say, 110 or 120 pounds, right? It's going to be about 1.5 times as much. So using METs is a way that we can compare one person to another. If I'm exercising at 10 METs versus somebody who weighs 120 pounds is exercising at 10 METs, I'm burning about 1.5 times the same amount, the amount of energy, right? So we can compare that to each other. Another way to calculate this is 3 milliliters of oxygen per kilogram of body weight. And that's 1 calorie per kilogram of body weight per hour. So I'm about 180 pounds. That's about 89 kilograms. So that means in 1 hour, I also burn about 89 calories at rest. So that is truly at rest. So if I'm sitting on the couch with my feet up, zoning out, watching TV, I'm burning about 89 calories an hour. And somebody else that weighs 120 pounds, which is around 55 kilograms, they will be burning that many calories per hour, right? If you weigh 55 kilograms, you're burning 55 kilograms or 55 calories at rest. So now if we know how many METs something are, we can compare one person to another and see how many calories they burn. So what we want to know is we can figure out how many calories does a 68 kilogram woman burn at rest in an hour. So the answer is 68 calories, right? Because it's 1 calorie per kilogram of body weight. Well, how many does she burn during a day at rest? Well, that's really easy. How many hours are there in a day? 24 times 68. So 68 times 24, and 68 times 24 is going to be... That's going to be 1,632. So then we have a 63 kilogram woman at rest, 24 hours a day, 1,632 calories. Very, very easy. Okay. Don't worry about figuring out how many METs you have to do. Somebody is doing, but that's very easy to calculate. So when we are measuring, but I'm going to go over it very quickly. So if we are measuring the volume of oxygen that this person breathes, right? And so that's how we do indirect calorimetry, remember? And we know that she is doing 29 milliliters per kilogram per minute, right? And resting, or 1 MET is 3.5 milliliters per kilogram per minute. Then all we need to do is divide 29 by 3.5, because 3.5 is rest, right? And so therefore, she's doing 8.3 METs. 8.3 METs. So we also know that she is doing 8.3 times 1 MET. Well, 1 MET is 68 calories, so 8.3 times 68. So she's exercising at VO2, that's a volume of oxygen of 29 milliliters per minute. We can then calculate that she's at 8.3 METs, and then we can calculate her total energy expenditure. So she's at 8.3 METs, 8.3 times 68 equals, she's burning 564 calories in an hour. Okay, so I'm not going to ask you to be able to convert calories per minute or calories per hour, but you should be able to do that. That's pretty much 7th grade math, right? If you calculate how many calories somebody is burning in an hour using your METs, if they work out for a half hour, it's a half of that. If they work out for 20 minutes, it's 2/3 of that, right? Or I'm sorry, 1/3 of that. Okay, so I'm not going to ask you to calculate walking or running energy costs, but just know that it can be done. Understand that these things are fairly constant, right? And so if we have a bigger person, right? If somebody again, I'm 180 pounds, so it's going to take more energy for me to walk or run on a flat or on a uphill compared to someone that weighs only 120 pounds, and I'm also going to be less than someone that weighs, say, 250 pounds, right? And those are very predictable, and we can calculate those with a high degree of accuracy. Okay, so again, you're not going to have to calculate these. Just understand that it's possible. Okay, don't worry anymore about this. Okay, so the American College of Sports Medicine, this is a supplied categorization of different exercises along with the approximate METs that you burn doing that, and so it'll give you some idea. Now it's obvious that there's a they can vary widely even doing the same activity, right? Go down to, say, basketball, right? So non-game basketball play, right? Just shooting hoops. As few as 3 METs, as much as 9 METs, right? If you're going hard, and game play is anywhere from 7 to 12. So I'll tell you right now that exercising at 7 or 8 or 9 or 10 METs is pretty vigorous. If you're not a very fit person who does cardiovascular exercise very regularly, you're not going to maintain that for very long. But you can look at these things and have a pretty good guesstimate of how many calories you personally burn doing any one thing, right? So let's use, for example, jumping rope, right? Jumping rope, anywhere from 8 to 12 METs, right? So if you weigh, say, 50 kilograms, so that's a small person, that's about 110 pounds, and you're jumping rope, you're going to be burning minimum of 8 times 55, right? You get the 8 from the METs, and the 55 times your body weight in kilograms, right? 8 times 55 calories per hour, or at the very high end, 12 times 55 calories an hour. And again, you can tell that that's a pretty wide range, right? Because 8 times 55, that's going to be 440, right? Whereas 12 times 55, that's 660. So that's still a pretty wide range. So again, this is just a guideline and really nothing more. Okay, another way that we can measure energy expenditure is we can measure how much work you're putting into something. So work is quite simply defined on a physics level as force times distance, right? So the amount of force it takes to push something and how far it takes to push it. And then we can express that total work in joules, right? So joules is force times distance times time. So if we move something that weighs 10 kilograms and we move it 10 meters, that takes a certain amount of work to do, right? So then if we want to see how long we push that block, that 10 kilogram block, we then can have total work done, or joules. So think about it, if force times distance is work, the amount of work we're doing. Think of that, if that were like miles an hour in your car, right? Then joules would be like total distance. The more you do work for the longer amount of time, the more joules you do. Okay, so that force times distance divided by time is power. Okay, and you can measure that on bikes in the gym. The most common ways that this is measured in the gym is either a bicycle in the gym or a rowing ergometer in the gym, the rowing machine in the gym. This is quite simply force times distance divided by time. Force times distance. So it's what you're pushing, how far you're pushing it, and how long you're doing, over what period of time. So that's power in watts. In watts, it's just the same as a light bulb or a vacuum cleaner or a blender or a microwave, right? That's expressed in watts. Power is expressed in watts. It's force times distance divided by time. Okay, so we can measure these watts, and watts is the amount of work done divided by the amount of time. Okay, so 1 joule for 1 second is 1 watts. So joules, the total work done, can be calculated by watts times time. And I'm not going to ask you to calculate this, but I would still like you to understand the concept, right? So basically, if watts is like miles an hour, joules would be like time. So if you go 50 miles an hour, then after 2 hours, you will go 100 miles an hour, right? If you go 100 miles an hour, then after 1 hour, you will go 100 miles. So think of that same type of relationship. Watts is how much work you're doing. So you take your watts times your time, and you got joules. Joules is the total amount of work you've done. So if someone runs 5 miles an hour in 1 hour, they'll cover 5 miles. If somebody runs 10 miles an hour in half an hour, they will cover 5 miles. And those people would burn approximately the same amount of energy in that time. Although the one person is burning twice the energy or burning it twice as fast, so it only takes them half as long. Okay, I'm not actually going to ask you to be able to convert joules to watts, so don't worry about that. Okay, so basically what I want you to understand is that energy expenditure is the primary way it's measured is going to be indirect calorimetry, which involves measuring oxygen consumption. If we know how much oxygen you're using, then we know how much energy you're using. Also understand that a way to generalize that and compare different people is to use the term METs, which is one metabolic equivalent, right? So we can use metabolic equivalents to explain how hard someone is going, how much energy they're using. And it's quite frankly, quite easily, their body weight in kilograms times the number of METs. That's how many calories they're burning. It's really very, very simple. And that one calorie per hour per kilogram at rest, that works for normal, healthy adults. It may be a little off in the very elderly, in the very young, or in people that have disease states. But for normal, healthy adults, it works quite well. All right, so understand indirect calorimetry, understand METs, understand that the person at rest burns their body weight in kilograms per hour. Understand that we can measure energy expenditure by measuring how much power someone puts out, and that our gym machines and things attempt to do this. Although now I'm going to tell you a little bit about the gym machines and the fact that they quite frequently overestimate how much you burn in an hour. And when I taught at San Diego State, we would do experiments on these, and they almost always overestimate. And I really think that they're designed to not be that accurate, possibly overestimate, quite simply because if people jump on a machine and it tells them they burn 500 calories, they're more likely to get on it again, and they're more likely to tell the local gym, hey, buy more of this machine, you know, this machine's great. If they notice that the elliptical machines are always busy because everybody's getting on them, then they're more likely to hop on that particular machine. So that's why I think they tend to overestimate. The problem with this is if you hop on a machine and it tells you burn 400 calories and you believe it, then you might have a 300 calorie muffin and you think that you have a 100 calorie deficit, right? When in fact you really only burned 250 calories and you had your 300 calorie muffin. So you actually have a 50 calorie positive energy balance when you're trying to lose weight. And so really do not trust these machines too much. They tend to overestimate by about a third. So I'm running up on the end of my 15 minutes maximum video time. So I'm going to go ahead and cut this off, and we will get started on the next one.